In stats today, we wrapped up sampling distributions of sample means. We talked about the central limit theorem and that n needs to be large in order for the sampling distribution to be normal. But there is one scenario where that doesn't have to be true, and that is right here. So before we talk about the central limit theorem, first look at where I drew the red arrow. If the population is stated to be normal, or somehow you know it's normal, then no matter what, you know that the sampling distribution will be normal. If you don't know the shape of the population, or maybe you know the shape of the population is skewed, in other words, it's not normal or it's unknown, then it needs to be larger than 30, larger than or equal to 30, and that's when the central limit theorem is applied. So this is applied in that scenario right there. So let's say something else. Let's talk a little bit more about this because people get confused between those two dashes there, and I think something more important happens. When n is small, my pen isn't working. There we go. The sampling distribution shape will resemble the population shape. So let's say I take a sample size of, I don't know, n equals 5. That's small. And I'm talking about the sampling distribution shape. Well, whatever shape the population took, sampling distribution will be very, very similar. So if there's positive skew, it'll be positive skew. If we don't know the shape of the population, then you can't really say anything. But what the central limit theorem is saying is when n is large, the sampling distribution is approximately normal. You know, that's the general rule, is large. In the stat world, they go with that. You see it's typed up here, is large. But for AP Stats, we need some concrete number to go off of. So that's why down here I wrote n is greater than or equal to 30. That way you have a nice concrete number to go off of, and it's easy to say whether it's normal or not. But don't forget that first dash right here. If the population is normal, the sampling distribution will be normal. And that's talking about the problem we worked in the last video right here, because it was normal up here. This one was workable and it had a small sample size. We were safe to say it's normal because the population was normal. All right, let's try one where that's not the case. So in this one, servicing air conditioners, company is maintaining air conditioners in this city, and over time, let's see, in the past year, it typically on average takes technicians 1 hour to fix them with a standard deviation of 1 hour. So nice typical or easy numbers to work with, but something stands out. Whoops, wrong button. I just totally messed up the screen. There we go, fixed it, sorry. This is a big deal right here, because when we see that, we should be asking ourselves, can we even work this problem? Because all we know in this class is using normal CDF. If you go on and take other stat classes, there are more distributions that you could choose from, but for this one, or for this class, normal CDF is about it, and we may be stuck. But look, we're in luck. They took a large sample. That means the sampling distribution will be normal. So it normalizes that right-skewed population. So let's write it out. The sampling distribution has a mean and a standard deviation. We're going to calculate a probability of an average work time of 1.1 or greater. We're concerned if this is going to be enough, like if it's likely or not, that it's going to take longer than 1.1 hours to finish a job. And the sample size is 70. So the mean of the means is the true mean. Standard deviation of the means is 1 divided by sample size. And we get 0.1195. So we talked about the center, the spread. Don't forget to talk about the shape. This is greater than 30. Make sure you say the phrase sampling distribution is approximately normal. All right, now we defined it. Now we're ready to write the question in proportion form. So probability of X bar being greater than 1.1. Then show your z-score, because we said it's normal, right? So we are doing a z-score. Some people get tripped up and they're like, when do I do the z-score thing? Well, if you say that the distribution's normal, we're going to do a z-score. So 0.1 divided by 0.1195, and we get a z-score of 0.8368. And you jump to normal CDF. And you get 0.2014. So up here, I don't know if they really wanted us to answer it. We could talk through it. Will it be enough? I don't think so. I think this supervisor will be upset because it looks like there's a 20% chance that jobs on average are going to take longer than 1.1. So that budget of 1.1 hours is probably not enough for the boss to be satisfied. All right, one more page. That's the end of the packet, but I just wanted to break all this down for you. So this is for sampling distributions. So the mean of the proportions is the proportion. It sounds so weird to say that, but that's the case. The mean of the means is the mean. Remember, those two are typed on your formula sheet, along with this next one. Standard deviation of the proportions is P times 1 minus P. Those parentheses do not look good. Divided by N. And for means, it is standard deviation divided by square root of N. Those two really trip people up because they may get a proportion problem and they can't find standard deviation because they're not given one anywhere in the paragraph. You got to literally derive it with that square root over there on the left. And then they jump to a mean problem, and it's obvious because you have a sigma and you divide by square root of N. But it's funny when you go jump between problem types, people get tripped up on proportions because in the paragraph there's no standard deviation, but that's because you're deriving it with P and N. So something that's true for both of those standard deviations only, or let's say this, or let's say these, sorry. I'm just going to start over. These are only true if n is smaller than 10% of the population. So we talked about that before. Standard deviations, those two standard deviation rules are only true if less than 1/10 of the population has been taken for a sample. All right, we also have shape. In proportion world, we have large counts. And that's in p greater than 10, in 1 minus p greater than 10. If true, then normal. And lastly, for means, we have the central limit theorem. And all that says is if n is greater than or equal to 30, then normal. All right, hopefully that makes sense. See y'all later.